All right, now we're going to get down to business and actually solve some differential equations. So you've actually seen example 1 before in 11.1. We solved this in 11.1, and if you recall, what we did is we treated this dy dx like a fraction and cross multiplied, so we ended up with dy is equal to 2 x dx. Okay, and then we can just integrate both sides. And we end up with y is equal to x squared plus c. Okay? Now, we're actually given some initial conditions here as well. So we can, given that y is 3 when x is 1, then we can substitute those values into this equation that we got and find out what c is. So 3 is equal to x squared, which is just 1, plus c. So that's telling us that c is equal to 2. And so our particular solution, particular solution for this particular problem, a solution, is going to be y is equal to x squared plus 2. Okay? So we did that before. In fact, I think we actually did an initial value problem for that and found, I think we had different initial conditions, but we did the same thing. So we're going to generalize this technique to be able to solve other kinds of differential equations, but just a particular type, ones in which the variables are separable. We call them separable. And they're separable if we can arrange the differential equation into something like this, all right, where we can get all the y terms on one side and all the x terms on the other side and integrate both sides. So let's take a look at example 2 because it involves an x and a y. So this one's pretty straightforward because we could just multiply both sides by y and multiply both sides by dx. And when we do that, what we'll end up with is y dy is equal to a negative x dx. And then we can just integrate both sides like we did before. So that's fairly straightforward. We end up with y squared over 2 is equal to minus x squared over 2 plus c. And we can actually rearrange that into, just by adding x squared over 2 to both sides, we end up with x squared over 2 plus y squared over 2 equals c. And I can actually rewrite that as x squared plus y squared equals 2c. So you might recognize that's the equation for a circle, right? If this was equal to r squared, right, 2c is essentially, it's just an unknown constant. So we don't even have to write 2c. We could just write it as, say, b, or there's some other unknown variable. But if that is equal to r squared, it's just you can see that it's an equation for a circle. And we actually looked at the slope field for this particular differential equation in 11.2, and you saw that we had those the slope field that was indicating some sort of concentric circles as the solution set for the differential equation. So there's a couple of differential equations we've solved, and I'll meet you for example 3.